Here we go. So continuing on with SN2, we talked about inversion and configuration. We talked about how an SN2 reaction is a concerted mechanism, that we have the nucleophilic attack and the loss of leaving group occurring simultaneously. Thus, it's a bimolecular reaction. Two components are colliding at the same time in the reaction. And now we're going to turn our attention to kinetics. So it says here that less sterically hindered electrophiles are going to react more readily under SN2 conditions, whereas tertiary halides are completely unreactive via the SN2 mechanism. Well, in order to rationalize this trend, what we're going to do is look at the reaction coordinate diagram, but I can make it what I think is even simpler. If we have a nucleophile over here, can you imagine that this nucleophile can attack the methyl halide? Well, this is my alpha carbon of a methyl halide. There's nothing in the way of that methyl carbon except for 3 hydrogens. That's very unhindered. So this reaction is going to occur no problem whatsoever. Similarly, if I try to do the reaction on a primary alkyl halide, a nucleophilic attack and loss of leaving group, the only thing blocking the alpha carbon is there's a methyl group at the beta position. So it's got a little something in the way, but not enough that it's going to be in the way all that much. But if we skip the secondary and go all the way to the tertiary, it cannot do an SN2 reaction. It stops. It can't do it. Why? Because the alpha carbon is so sterically hindered by 3 methyl groups in the way that it just can't get in there to attack it. And if you're thinking, well, why doesn't it go around to the other side? It can't do that either. It's too sterically hindered. And that's why we're mostly going to see SN2 chemistry occurring with methyl halides and primary alkyl halides. It can occur with a secondary halide, but there is a caveat to that, which I'm going to show you in a little bit. Let's take a look at some numbers here. It says alkyl groups branching from the alpha and beta carbons hinder backside attack, right? They encumber it. It's too difficult for the nucleophile to get to that electrophilic center. Let's take a look at the left side of this table, the effect of an alpha substrate. This is what I was showing you on the last slide, okay? It says if you try to take an alkyl bromide and treat it with iodide and acetone at 25 degrees Celsius to do an SN2 reaction, what's the relative rate? Well, if we have ethyl bromide, so we just have that little methyl group at the beta carbon, the relative rate, they assigned a value of 1. And so if we look at methyl bromide as opposed to ethyl bromide, it's only got 3 hydrogens attached to the alpha carbon, so it's 145 times faster. But then once you have 2 or 3 beta substituents, it basically becomes useless for a substitution reaction because the nucleophile can't get in there, right? The nucleophile cannot attack because it's too hindered by 2 or even 3 alkyl groups. It can't get in there. Give me a thumbs up if you follow me on that idea, that the nucleophile cannot get to the electrophilic center. Okay, when we have, a secondary or tertiary alkyl halide, which is what we have here, secondary and tertiary, it just can't get in there. But even if you have a primary alkyl halide, so this is primary, this is methyl, if we turn our attention to the right side of the table, it's looking at the effects of beta substituents. If you examine every single one of these, this is a primary carbon, this is primary, they're all primary. Let me try to delete this. So these are all primary alkyl halides. Everything in here is primary. However, you see that branching at the beta position or substitution at the beta position also has an effect as well. Check it out. If we have, if we assign ethyl bromide a relative rate of 1, if you put 1 substituent on the beta carbon, yeah, it slows it down a bit, but not much. Once you get 2 or 3, then the reaction becomes super slow to the point where it's almost useless. And so that is why we can't just, and that's why your instructor can't just say to you, okay, everybody, I want you to memorize that a primary alkyl halide always undergoes an SN2, because it's not always true. If you have enough beta branching, it doesn't work with that either, or it's going to be super duper sluggish, really not useful for chemists. Chemists want reactions that are going to occur at an appreciable rate. Now, if we look at the reaction coordinate diagram and we look at the transition state, it says here, what feature of this diagram is relevant to rationalize the rate of the reaction? Well, what's related to the rate of reaction that we see here? It's the activation energy. So we look at the activation energy here. And it says, what feature is relevant to rationalize the thermodynamics? That's the relative energies of the reactants and the products. But let's get back into the whole kinetics thing. If we see what's happening here, we have methyl bromide, and it's undergoing a nucleophilic attack from a cyanide ion, like this. So we have nucleophilic attack and loss of leaving group, but this is our transition state up here. And since we just have methyl bromide, right, there's no branching at all on the alpha carbon, and so the SN2 is going to go really well. However, what's going to happen if we have a secondary or a tertiary alkyl halide and we try the same reaction? How is that going to affect the rate of the reaction? Well, we can see that if you go from a methyl substrate to a primary to a secondary, the activation energies go up and up. And activation energy is directly related to reaction rate. So a methyl is going to react the fastest. This will be the fastest. And the secondary would be the slowest. If you're wondering, well, where's the tertiary? That's not even on here. Tertiary substrates are so slow you can't even measure it. It doesn't even work at all. So the rationale, again, and I know I'm saying this for probably the 5th time, but whatever. It's worth repeating. The rationale is that the more substitution that you have at the alpha carbon, the harder it gets for the nucleophile to come in and attack that electrophilic carbon. And that's why methyl and primary substrates, they work really well for SN2 reactions, whereas a secondary substrate, meh, it can give you some product, but it actually will mostly give you elimination. And we'll talk about that in a little bit. So something you can remember is that if you have a primary or a methyl substrate, it's going to undergo an SN2 reaction when treated with a strong electrophile, or sorry, a strong nucleophile. Now, going back to the whole idea of beta branching, it says draw the structure of neopentyl bromide. Well, I didn't even include that in here. I'll draw it for you just to kind of show you where it is, to help you out. This is neopentyl bromide right here. Like we can just scribble the name in here. Neopentyl bromide. All right, we don't even cover the neopentyl group when we're practicing our nomenclature, so don't worry about it. We'll just scribble the structure in here. So neopentyl bromide looks like this. There's my black pen. So it looks like this. Okay, so we draw neopentyl bromide. Is neopentyl bromide primary, secondary, or tertiary? Well, what they're getting at is that it is a primary carbon. Why? Because the alpha carbon is only attached to one carbon. Right? That's my alpha carbon. This is my beta carbon. So it is a primary alkyl halide. Should neopentyl bromide react by an SN2 mechanism relatively quickly or slowly? And the answer is it's going to react very slowly. Why? Because of exhaustive beta branching. And that is why we can't always just memorize everything in organic chemistry. Sometimes we have to go beyond just memorizing some rules. Yes, most of the time a primary and a methyl alkyl halide will undergo an SN2. However, this would be an exception. This would be an exception. Why? Because it's got so much beta branching that it renders this alpha carbon sterically hindered. So it's a good idea to always understand things in organic chemistry rather than just simply memorizing them. Is there some memorizing to do in organic chemistry? If I said no, I'd be a liar. So yes, there is some. However, oftentimes we need to understand the rationale. Section 7.4, moving on and talking a little bit more about nucleophiles. We've talked about nucleophiles and electrophiles even way back in chapter 6. So if you need to go back and look at nucleophiles, you can cover that in section 6.7 of our textbook. However, it says here that a strong nucleophile is what's needed for an SN2. How do we know that we've got a strong nucleophile? Generally speaking, it's going to have a negative charge. If you compare Hydroxide versus water, well, they're both nucleophiles, but hydroxide is a strong nucleophile because it's got a negative charge on it. And water is a weak nucleophile. It doesn't have a negative charge on it. If you compare the rates of these two SN2 reactions with water and hydroxide acting as the nucleophile and methyl iodide acting as the substrate, when you have the hydroxide, it reacts really fast, whereas if you're trying the reaction in water, it works really, really slowly. And so you should be able to recognize a nucleophile as being strong or weak. Strong nucleophiles are things like hydroxide, methoxide, ethoxide. The hydrosulfide would be a strong nucleophile. There are others that we're going to see throughout the class, like, a cyanide would be a good one. Iodide, bromide, chloride. I have these listed on another slide, I think. Iodide, bromide, chloride, etc. In fact, I think I have them on a table right here. So you need to have the strong nucleophiles memorized. I would know all these. I think I had all of them on here except for the thiolate, but anyhow. So these are all the strong nucleophiles. What's a weak nucleophile? An alcohol, excuse me, or water. Those are both crummy nucleophiles. All right, so there we go. Strong nucleophiles prefer SN2. In general, anions are strong nucleophiles, and the more polarizable an atom is, the better nucleophile it is. Remember that polarizability is something we discussed in chapter 6. Polarizability is just the ability of an atom or an ion to distort its electron cloud in response to its environment. And since, if you were to compare iodide and chloride, which one is more polarizable? Well, it's iodide, because iodide is in the fifth period. It's much bigger. The electrons, the valence electrons, are much farther from the nucleus. They can distort their electron cloud, and so it can kind of shape itself to attack an electrophile. But that's what polarizability is. If you were to compare the polarizability, let's say, of hydroxide and hydrosulfide, well, hydrosulfide, HS minus, is a better nucleophile because it's more polarizable. The sulfur atom is bigger, it can distort its electron cloud, and so that's kind of a rationale there. But besides these reagents, we also have to take into consideration a solvent, because a solvent can also affect nucleophilicity, and that's something that we're going to look at in detail a little bit later. All right, so that covers SN2 for now, and now we're going to get into E2 reactions. I haven't drawn the mechanism of an E2 yet. I mentioned it when we were talking about substitution versus elimination, but now I'm actually going to go over the mechanism of elimination with you. And you can imagine that if we have an E2 reaction, the E stands for elimination, and it does, and the 2 stands for bimolecular. Bimolecular. Or you could put second order, or you could say E together. That means that we have a proton transfer and a loss of leaving group occurring simultaneously. How do you know that you can get an E2 reaction? We'll take a look. It says when an alkyl halide is treated with a strong base, it can undergo beta elimination, which we also call 1,2 elimination, to form an alkene. So what you do is you look at the alpha carbon with your halogen on it. Go to a beta carbon. If a beta carbon has a proton, the base can come in and take that proton. The pair of electrons between the carbon and the hydrogen are going to form a pi bond, and then we lose the leaving group like that. All together, the proton transfer, the formation of the pi bond, and loss of leaving group. Here it is drawn down here from our textbook. We have the base taking a proton, and we have the loss of leaving group occurring simultaneously to give us an alkene. An elimination reaction. We're eliminating something from the molecule. What did we eliminate? Look very carefully. Here you have X and H. Here they are over here. They are not in the alkene, so you eliminated them from the molecule to make the alkene. Well, if we look at the kinetics of an E2 reaction, since it's a bimolecular reaction or a second order reaction, the rate is going to depend on the rate constant multiplied by the concentration of our substrate, our alkyl halide, and the concentration of the base. This is the same rate law that we saw for an SN2 reaction. Exact same thing. The only difference is that an SN2 reaction is substitution and an E2 reaction is elimination. That's all there is to it. Now, if we think about a reagent like sodium hydroxide, we also saw that sodium hydroxide is a great nucleophile. So which is it? Is it a nucleophile or is it a base? Like you talked about it in general chemistry 1 and 2. Well, the answer is it depends on the situation. If we have a sterically hindered substrate, then our hydroxide is going to act as a base. If we have an unhindered substrate and we have a good leaving group, then the hydroxide would act as a nucleophile. So check it out. If we have a really hindered alpha carbon. So here's my alpha carbon. You see you've got 1, 2, 3 big alkyl groups on it. The hydroxide cannot go in and do a backside attack. It can't act as a nucleophile here. However, if you think about all 3 of these methyl groups, they all have just protons dangling off. And the base can pull off one of those protons because the proton is kind of like sticking out like this. And so what it can kind of do is just kind of pluck off the low-hanging fruit, so to speak, something that's sticking out a little bit further like that proton. So when it pulls off that proton, these electrons are going to form a pi bond and you're going to lose a leaving group. And that is why when you have a hindered substrate, E2 elimination is going to predominate when we have a sterically hindered substrate. And so what have we got? A strong base, a strong nucleophile like sodium hydroxide will give us an SN2 reaction with a primary alkyl halide, but will give us an elimination reaction with a tertiary alkyl halide. Well, let's take a look at this reaction here. This is an elimination reaction. It tells us here that this is a second order rate equation. That means that this must be an E2 reaction, right? It's an elimination. What we're losing is H and chloride, right? We're losing H plus and chloride. Anyhow, yeah, I'll just leave it like that. What you end up with is water and sodium chloride in the end, but that's neither here nor there. Let's start by drawing out the mechanism for this reaction. So I'm going to start by drawing my chlorocyclopentane or cyclopentyl chloride, either way. So here we go. This is my alpha carbon. I go to the beta carbons. This is a beta carbon. This is a beta carbon. Since there is a plane of symmetry down this molecule, both of the beta carbons are identical. So I'm just going to highlight one of them, and I'm going to pencil in one of the hydrogens on that. Now remember, this is a secondary alkyl halide. It's not primary. It's not methyl. So SN2 is not going to predominate. The elimination will predominate. I'm going to draw my hydroxide. My hydroxide is my base. The base is going to grab a beta proton. Then it's going to form a pi bond, and we're going to lose the leaving group like this. And we end up with the product, which is called cyclopentene, plus we end up with water and sodium chloride. Like this, I guess I should put my sodium ion over here. So what do we see? We see the proton transfer and the loss of leaving group occurring simultaneously. So in A, it says what happens to the rate of if the concentration of the chlorocyclopentane is tripled and the sodium hydroxide remains the same? Well, if our rate law is rate is equal to the rate constant multiplied by the concentration of our substrate multiplied by the concentration of hydroxide, that means it depends on the concentration of both. So in A, we have rate is equal to K multiplied by chlorocyclopentane is tripled and sodium hydroxide remains the same. So we'll leave it still at 1. So what's going to happen to our rate? It's going to be 3 times faster. Okay, let's move on to B. In B, it says what happens to the rate if the concentration of the chlorocyclopentane stays the same and the concentration of the sodium hydroxide is doubled. Could anybody answer that one for me? What would happen to my rate then? Go up, down, how much? What would change? Could anybody answer that one? Yes, thanks, Luke. It's going to double, right? Rate, we'll just write here, rate would double. And for the last one, it says what happens if the concentration of chlorocyclopentane is doubled and sodium hydroxide is tripled. Can anybody tell me the answer to that one? So double and triple. What would happen to my rate then? Exactly. Thanks, Luke. It would be K, 2, and 3. 2 times 3 gives you 6. So it'd be 6 times faster. Thanks, Kiana. Thanks, Angel. Absolutely. You're all 100% correct. So there you go. Bimolecular reactions, an E2 reaction and an SN2 reaction. What do they both have in common? They're both second order reactions. Now, if you're wondering, Mr. Dion, do you have a table somewhere that's going to summarize, the type of substrate and whether SN1 SN2 or E2 is going to predominate? Well, that's something that we're going to look at in a little bit, but let me just go ahead and I'll show you where it is. It would be down here, and we're going to see this in class on Thursday. We're going to talk about this table here. So let's say you have a strong base, strong nucleophile, like a hydroxide, and you have a primary substrate, you're going to get almost all SN2. If you have a methyl, you're only going to get SN2. If it's secondary, you get mostly elimination, and if it's tertiary, you only get elimination. So we're going to look at this table in detail later on. But again, in case you're wondering, hey, is there a summary of this information? The answer is yes, and we're going to look at it in the next class. We won't have time to get here today, but yeah, it's in there. All right, well, let's move on, and let's talk a little bit about alkene stability. So I'm going to go grab my model kit, since we might need this. And, why did we talk about alkyl halides? Because in the substitution and elimination reactions, our substrate was always an alkyl halide. So that's good. Now, why are we talking about alkenes? Why are we switching? What's the point of this? Well, what do we get from elimination reactions? We make alkenes. And so now we're going to turn our attention to alkenes and talk about what makes an alkene stable versus an unstable alkene. It says here that because of steric strain, cis isomers are generally less stable than the trans. And I think that most people can just see this from this space-filling model that's on this slide, that if you have trans 2-butene, since the two methyl groups are further away from each other, there's less steric hindrance compared to if you have the two methyl groups on the same side, right? They're kind of in each other's way like that. Give me a thumbs up if you follow me on that. Is everybody with me on trans would be more stable than the cis? Just because it's kind of got more room, right? Okay, cool. So this is a good rule that you want to memorize in general. A cis isomer is going to be less stable than a trans. Okay, cool. And what's neat is you can actually quantify this. How cool is that? If you compare the heats of combustion of trans 2-butene and cis 2-butene, look at the difference. It's not big, but they are both exothermic reactions. They're just combustion reactions, but you see there's a difference of 4 kilojoules per mole between the two, and you see that the cis actually releases more energy. What does it tell you? It was less stable to begin with. The less stable something is, the more energy it's going to release when it undergoes combustion. So this one, the cis, more stable by 4 kilojoules per mole. It's not a lot, but it's a little bit. And now if we look at a graphical representation, one thing I like about teaching science is that there's always somebody in the class who just, give me a graph. I need a graph. Show me a graph of everything. I need a graph for this. I need a graph for that. Well, if you look at the enthalpy and the change of enthalpy for the two here, you see there's a difference of 4 kilojoules per mole, and that the trans is more stable. So more stable than the cis. So that's kind of cool. And besides cis and trans stability, we can also go deeper on our alkene stability and talk about hyperconjugation. Remember hyperconjugation? I went over it with you when we were discussing carbocations. And I said a tertiary carbocation was more stable than a secondary, than a primary, and a methyl was the least stable. Why is that? It's because alkyl groups can stabilize a carbocation. Well, alkyl groups can also stabilize a carbon-carbon pi bond by hyperconjugation. And so what you need to know as an organic chemistry student is that if you go from ethylene, which is this compound, where it's just surrounded by 1, 2, 3, 4 hydrogens, as you start putting alkyl groups 1, 2, 3, and 4, the double bond becomes more stable. So our alkene gains stability. The take-home message of this slide is nothing more than this. More alkyl groups means you've got a more stable alkene. And this is going to be very important when we look at elimination products that are called Zaitsev products. Zaitsev, so this is named after a scientist. And Hoffman products. Hoffman products. It's very important that you understand that the more substitution we have on a double bond, the more stable that double bond becomes. Well, with that in mind, let's see if we can just answer a quick question that deals with alkene stability. These are all isomers of each other. If I call this first one A, I call this one B, and I call this one C, could anybody tell me which of these alkenes is the most stable? Which one would be the most stable alkene here? Yes, absolutely. Absolutely, it's going to be A, isn't it? Why is it this one the most stable? Because if you look at the 2 carbons in the double bond of each one of these, okay? Here's the 2 carbons in the double bond. In A, every one of those carbons in blue is attached to a carbon. 1, 2, 3, 4. This is tetra substituted. Therefore, this is the most stable. Could anybody tell me which one of these would be the least stable? B or C? Which one would be the least stable? Yeah. Yeah, it's going to be B, isn't it? Look, if we see how many total carbons this double bond is attached to, it's only attached to 1, 2. C is attached to 1, 2, 3. Put another way, here we have 2 hydrogens attached to the carbon, and here we only have 1. So in B, it's di-substituted. So di-substituted. Therefore, this is the least stable. And this one is tri-substituted. Tri-substituted. And so it's somewhere in between the two. So A is the most stable, and B is the least stable. There we go. Alkene stability. So now you know the more R groups you have surrounding your double bond, the more stable it becomes. Well, let's turn our attention to cycloalkenes for a second. Cycloalkenes. We're not going to spend a lot of time on cycloalkenes, but something that an organic chemist should be aware of is that if you have less than 7 carbons in a ring, the only way a double bond could exist in a ring is for it to be cis. Okay, if you look at cyclopropene, you see the 2 hydrogens are on the same side of the double bond. Same thing in cyclobutene, in cyclopentene, and then in cyclohexene. It's not until you get up to 8 carbons that you could have a trans double bond in a ring. And when you apply this rule, so it says here, so we do not need to indicate if the alkene is cis or trans unless the ring contains 8 carbons or more. That otherwise, it's a given that it's going to be cis. And when you apply it to bridged bicycloalkenes, it's called Brett's rule. I'm just going to write here on the slide, will not ask. I'm not going to ask you anything about Brett's rule, so don't even worry about Brett's rule. I'm just going to skip it. And that brings us to section 7.7, where we look at the regioselectivity of elimination reactions. The regioselectivity of an elimination reaction. What does the word regioselective or regioselectivity mean to you? To me, it means I've got a region and I'm going to select one region over the other. right? It's selective for one over another. And if we look at this substrate here, we have a tertiary alkyl halide, and we're treating it with a strong nucleophile, strong base. Remember, a tertiary alkyl halide is not going to undergo an SN2 reaction. It's only going to undergo an E2 reaction. So we're going to make an alkene, but you see that we end up with two different alkenes. One I call the Zaitsev product, and one I call the Hoffman product. And in order for us to get a mixture, or why do we get a mixture here? It's because we have more than one type of beta carbon here. Check it out. If you look at this substrate very carefully, this is the alpha carbon, this is a beta carbon, this is a beta carbon, and this is a beta carbon. Why did you use two different colors? Why did you use blue and black? Well, the two that I have highlighted in blue are both methyl groups, whereas the black one is a methylene. Are you with me on that? But remember that they both have hydrogens attached to them. The one on the black carbon has a hydrogen. It actually has two hydrogens, but I'll just pencil in one. And the ones in blue, they also have hydrogens on them. So I'm going to pencil in one here. If my base removes the blue proton, so let's imagine that my sodium ethoxide removes the blue proton. I'll just draw it like this. So removes the blue proton, I form the double bond and lose the leaving group. I'm going to end up with this product, the Hoffman product. Whereas if my base removes the proton in black, if I remove the proton in black, I'm going to end up forming my double bond here, and I'm going to end up with the Zaitsev product. Can everybody give me anybody give me a thumbs up? Do you see the difference between these two mechanisms? Just two different types of beta protons give you two different products. Okay, so you're probably wondering, and it would be a good thing to wonder, well, which one am I gonna get more? Is it gonna pull off the blue protons or the black protons? It says here at the bottom that when you use ethoxide, you get two products. You get both of them. You get the Zaitsev product and you get the Hoffman product. Do you notice the difference between the two? The Zaitsev product is the more stable alkene. Why is that? Because if we examine the Zaitsev product, we highlight the two carbons here, you see that the Zaitsev product is 1, 2, 3 tri-substituted, whereas the Hoffman product is only di-substituted. So Zaitsev is more stable than Hoffman. Zaitsev is the major product in this case, and Hoffman is the minor product in this particular case. Not always, but in this case, it is. So we say that the E2 elimination is regioselective. It's selective for the formation of the Zaitsev product. It's selective for abstraction of this proton here. Again, we can practice drawing our mechanism. We're going to abstract that proton or remove it. We form a pi bond and we lose our leaving group to make mostly the Zaitsev product. However, we do remove some of the blue protons to make, about 30% of the Hoffman product. So when you can get constitutional isomers like this, and you get a mixture of them where one of them is the major, one of them is minor, we say it's regioselective. You might be wondering, is it always regioselective for the most stable alkene, the Zaitsev alkene? The answer is no. Sometimes it is, sometimes it isn't. It depends on the situation. And we can actually control this regioselectivity by carefully choosing the base. We choose a base, and depending on that base, we can either get the Zaitsev product or we can end up with the Hoffman product. We can kind of control nature, so to speak. We can get the product we want just by picking the correct base. Are you ready to look into, well, how would I pick the right base? Check it out. I think it's pretty rational. It says here, if you look at this table, the data in here shows that the more bulky or sterically hindered a base is, the more it's going to favor the Hoffman product versus the Zaitsev product. If you have an unhindered base, it's going to make the Zaitsev product. Now, why would that be? Well, remember that this is the more stable alkene, right? Because it's more substituted. It is more stable. So if the base can form the more stable compound, it will. right? If we go back to our substrate, you have the black protons. If you pull that off, you get the Zaitsev product. Then you have the blue protons. If you pull one of those off, you end up with the Hoffman product. If you choose a small base like ethoxide, ethoxide's structure is just this, an ethyl group with an oxygen with a negative charge. If it goes to pull off this proton here, this one is dangling off the end of a methyl group, right? It's just hanging on that methyl group. Whereas if I try to pull one off of this methylene here, you can see that the methylene has got this branch on it and it's got all of this over here. So it's harder for the base to get in and pull this off. Whereas if you look at the blue proton, if you look at the blue proton, all it's got is just this whole one thing attached to the carbon to which it's attached. So it's kind of more available to be pulled off. But again, even though it's more available, if it pulls off this one, it gives you the more stable alkene. And so if you have a stealthy base, a really small base like this, it's going to preferentially pull this off to give you the Zaitsev product. Whereas if you have a big bulky base, like this one here, this is called, so this is ethoxide. This one is called Tert Butoxide. Tert Butoxide is so sterically hindered, it would pull this proton off if it could, but it's just so dang sterically hindered that it doesn't. It's like, I'm so giant, I'm just going to go for the low-hanging fruit. I'm going to pull this off, and that's going to give me the Hoffman product. You see this manifest in the numbers here. If you use ethoxide as your base, you get 71% of the Zaitsev, whereas if you switch it to Tert Butoxide, you get 72% of the Hoffman. And if you have an even more hindered base like this, get a super high yield of the Hoffman with very little Zaitsev. It's all about the proton availability. Again, if we look at the black proton and look at its alpha carbon, it's attached to all this and all this. It's more sterically hindered than if we look at the alpha carbon where the blue proton is. It's only attached to one group, so it's more available. Are you with me on that? Give me a thumbs up if you follow me. If you don't, stop me and ask me a question. Zaitsev versus Hoffman. A small unhindered base is going to give you the more stable alkene, even though the proton is more hindered. And if we have a hindered base, it just goes for the low-hanging fruit, the most available proton, and it just gives you the more unstable, or the less stable, I should say, alkene. All right, so that deals with regioselectivity. So again, this is just rehashing what I just went over with you. Why does that big bulky base like Tert Butoxide, which usually has potassium as its counterion, potassium T-butoxide, why does it favor Hoffman products? Because a sterically hindered base is going to pick off that low-hanging fruit, that proton that's dangling out there in space, so to speak. These are some other hindered bases besides potassium T-butoxide. We can use diisopropylethylamine or triethylamine. This is the hindered base that my students like the most. My students like to use this about 99.999% of the time. So every 10,000 questions, I might get somebody bringing up one of these. But they generally like this. And the acronym that we use for this is just T for Tert, and then we write BUO. So that's the butoxide or Tert Butoxide. And then the K is for the potassium. Okay, so that's where that comes from. I like that. And then diisopropylamine and triethylamine, they also have acronyms. Diisopropylamine, we use diisopropyl. No, actually, maybe there isn't one for this. I think you would use something like, I can't think of an acronym for this. But for triethylamine, I can. You use ET for ethyl. You put a subscript 3 because there's 3 ethyl groups, 1, 2, 3. And then you just put your nitrogen like that, triethylamine. You can also call it TEA, triethylamine. Same thing. It's just an acronym for it. But again, my students love potassium T-butoxide, and I don't blame them. It's the one that's used most frequently in our textbook. So what we're going to do next is we're going to take a look at this question, which deals with some E2 reactions. We've got tertiary alkyl halides for all of these. And so we know that substitution is not going to occur in any of these reactions. And we're treating them with ethoxide, which is a strong base, hydroxide, which is a strong base, and Tert Butoxide, which is a strong base. The difference is these two are non-hindered, whereas T-butoxide is a very highly hindered base. It's a big, bulky base. So let's start with the first one. If we examine this compound carefully, here is my alpha carbon. I've got three kinds of beta carbons. I've got this methyl group, I've got this methylene here, and then I have this tetrasubstituted carbon here. I cannot use the black carbon at all because there's no hydrogens attached directly to it, so I'm just going to delete that. Therefore, I've got what? I've got these blue protons here, and I'm going to use, why don't I just use black for this one here? Okay, I've got the blue proton and the black proton. Keep in mind, I've got a tertiary alkyl halide, and I have an unhindered base. Unhindered base. If I have an unhindered base, which proton is it going to pull off preferentially, the black one or the blue one? Could anybody tell me the answer to that? If I have an unhindered base, what do you think I'd pull off? You know what we could do? Yes, absolutely. Both of my students are correct. I'm going to pull off the black proton because it's more hindered, right? If you look at the alpha, if you look at the carbon that this black hydrogen is attached to, it's attached to, you know, you kind of get all this group over here and all this group over here. Whereas if you look at this one here, it's only attached to one group. So the black one is more sterically hindered, and it's going to produce a more substituted alkene. Don't believe me? Well, let's try. If we had our ethoxide, I'll draw it here, ethoxide. There's our base. If it was to pull off the black proton, the mechanism would be proton transfer, form a double bond, lose the leaving group, and what we'd end up with would be this, where we have our six-membered ring. Our double bond is here. We still have this methyl, and we have two methyl groups over here. If I was to pull off the blue proton, I'm going to erase my curved arrows now. So erase this one, and this one. If I pulled off the blue proton, it would look like this. I'm going to pull off the blue proton, form a double bond here, and lose my leaving group. And in that case, I'd end up with this alkene, where I have my six-membered ring. And now my double bond is going to be here. So which one of these is the Zaitsev product and which one of these is the Hoffman product? This is my Zaitsev product because if you look at the two carbons in here, they're attached to a total of 1, 2, 3 carbons. If you look at the two carbons in here, they're only attached to 2 carbons. So since this is the most stable alkene, this is the Zaitsev alkene, and this is the Hoffman alkene. Well, if I have an unhindered base, it's going to produce the Zaitsev product as the major product. So I'll put here major product, and the minor product, like that. So what I would like you guys to do is I'd like to give you a short break, and I'd like you to tackle these two questions. If you look at the alpha carbon on both of these, you'll see that there's two types of beta carbons. There's the methyl groups that have these protons, and then there's the methylenes that have these protons down here. In both cases, you're going to get the Hoffman and the Zaitsev product, but which one is going to predominate? If I use sodium hydroxide, I'm using an unhindered base, whereas if I'm using potassium T-butoxide, I'm using a hindered base. All right, so we're going to take a short break, and then we're going to come back, and we're going to tackle both of those problems. So I want you to give it a try and see if you can draw both of the products and determine which one is the major product in each case, and also see if you can draw a mechanism for the reaction.